today I'm going to talk about their relations to entanglement entropy in quantum field theories. So part of my talk is devoted to the relation between entanglement entropy and also renormalization group flow. And the second part will be supersymmetry theories. Supersymmetry. And where I will introduce a new quantity, so I will call it supersymmetry entropy. And where I will use the localization technique to compute them. So okay, let me start with the first part. Okay, so here I'm going to consider quantum field theories and two quantum field theories. So yeah, and whose are interpreted by some RG flows. So you have two fixed points of the renormalization group flow. So one is a BUA fixed point, so where you have UV CFT, and also you have IR CFT here. And they somehow are interpreted by some RG flow. And so UV fixed point is realized when energy is very large. And on the other hand, if you lower the energy, then you are at the IR fixed point. So, so in such a situation, so I'd like to ask one question. So is there any quantity which measures the degrees of freedom in quantum field theory? So I'm going to consider some function. It is called C function. So this is the monotonically decreasing. Monotonically decreases under any RG flow. So is there such a function in quantum field theory? So if such a function exists, then so you can use this function as a measure of degrees of freedom. So here, okay, so this function C, I will denote it C, and I plot it as a function of inverse of the energy. Then so C starts with some value at the UV fixed point, and also it monotonically decreases along the RG flow. So and it approaches to the IR value. So this is the RG flow. So intuitively, so the degrees of freedom should be monotonically decreasing along the energy as you lower the energy, because the massive degrees of freedom are decoupled as you lower the energy. So intuitively, so you should have such a function as a measure. Okay, so such a function, C function. So this is a measure of degrees of freedom. Okay, so yeah, we'd like to consider such a quantity, and there are several examples. In 2 dimension, there is a very famous theorem by Zamochkov. And it is called the C theorem. Okay, where so he claims that the central charge, so in 2 dimensions you have a conformal anomaly, and he proved that the central charge decreases under the RG flow. So if you compare the central charges at the UV fixed point and that's of the IR fixed point, then the UV value is always larger. Okay, so this is the Zamoransky theorem. And also, here is the A theorem. So A theorem was conjectured by Cardy many years ago, 88, and recently proved by Sohar and Schwimmer. So the claim is that, in 4 dimension you have 2 central charges. One is called A and the other one is called C. And A is the coefficient in front of the Euler density. So in 4 dimension, A is supposed to decrease under any RG flow. And the proof was given by Zohar and his collaborator recently. So we have an example such that it multiply decreases under any RG flows in even dimensions. But our interest is in...
Sorry, well, is A defined along the RG flow?
I think, they constructed an express function. In between,
It's well defined.
So in both cases, there is an interpolating function. So between UV and IR fixed points. And in 2 dimensions, Zamoransky have such a function, Zamoransky C function. And also in 4 dimensions, recently they constructed nice functions, so which coincide with the A anomaly at the fixed point. Okay, so today I'm going to talk about their relation to the entanglement entropy, and I want to start with a construction of 2-dimensional C function by using entanglement entropy. So let me start with entropic C function in 2 dimensions. Okay, so to define such a C function in 2 dimensions, so I will consider an entanglement entropy of an interval of width R. So this is my region A, and both sides are B. And I will call the entanglement entropy of an interval as S of R. So this is a function of R. Okay, so this is the entanglement entropy. So then I define an entropic C function as follows. So entropic C function is defined by taking a derivative with respect to R of the entanglement entropy, and I multiply R again. Okay, so I define some function made of the entanglement entropy of an interval in 2 dimensions. So this is 1 plus 1 dimension. So I'm going to show you that this function Montevideo decreases along any RG flow. Okay. Okay, so before that, let me remind you that if theory is conformal, so for CFT2, so last time I showed you that there is a log divergence in even dimensions, and where, okay, and in 2 dimensions you have only log divergence, log divergent term, and whose coefficient is given by the central charge of CFT2. Okay, and here epsilon is UV cutoff. This is UV cutoff. And this is the central charge. Okay. So then, my entropic C function. So entropic C function satisfies the following properties. So the entropic C function satisfies that if theory is conformal, then the entropic C function is equal to the central church. So it is clear that when theory is conformal, then the entropy is given by this formula. And if we substitute this guy into the definition, since I multiply 3, then it gives you the central church at the fixed point. Okay. And also, this is one non-trivial. So the entropic C function, if we take a derivative with respect to R, then it is non-positive. Okay, so once you identify the length or width of the interval with the 1 over the energy scale, this means that the entropic C function Montague decreases along the energy flow. Okay, I identified R and 1 over energy. Okay, is it clear? Okay, I'm going to show you the second property. Okay, the proof of the second is given by Cassini and Crater. Okay, I'm going to show you the proof. And given by Cassini and Crater. Years ago. So basically, they use the strong subjectivity of the entanglement entropy. So I will denote it as SSA, and also they take advantage of Lorentz invariance of the theory. And then the second one follows from there. And okay, let's consider. So this is the spatial direction, and this is time, Euclidean time direction. Or in this case, I think this is Lorentzian time. Yeah. Okay, and then, so first, I have constant time. At constant time, I have an interval with a small r. And at the different time slice, I have another interval whose width is capital R, and then I take a region A and region B in the boosted frame. Okay, this is my region A, and this is my region B in the boosted frame. Okay. So here, since I have a Lorentz invariance in my theory, so I can boost interval at constant time to this guy. So to this one, and then this part becomes the union of A and B. Okay. So because every information going through region A and region B has to go through this slice. So that's why this is the union of the two regions. And also, so this part is an intersection of A and B. Because every information, every particle going through this slice has to go through both A and B. So this is the intersection, okay? Is it clear? Okay, so my figure is actually very bad because, okay, so this is supposed to be a light cone, so t equal to x. This is supposed to be the light cone, and this is also writable. Okay, then so we are going to use the strong subjectivity. So strong subjectivity tells you that. So this one tells you that the entropy of the union and also entropy, the sum of the entropies of the union and intersection should be less than entropy for A and entropy for B. So I'm going to use this inequality. Okay, so apparently this one is equal to S of R, capital R, because the union has a length capital R, and the intersection has the value, so S of small r. Okay, so these two are very trivial. But, okay, so this one, so SA and SB are equal in my figure, and this gives you twice the S of the square root of small r times capital R. So because if you compute the invariant length of the A and B, then you see that this is a length. This is the length. Okay. So then now I will take some limit where small r is very close to capital R. So here, I'm sorry. So this is not equal to the UV canton, but yeah, you can have another small number, delta. So delta is very small. And if you choose R in this way, then you can expand this inequality with respect to small delta. And at the second order of delta, then you see that, okay, can you see this line? Okay. And then, so you can show that the derivative of the entanglement entropy, entropic C function is negative. So the derivative is equal to S prime plus R times S second prime, and this becomes 0. Sorry, this is less than 0. So this inequality follows from the strong subjectivity. So this is a proof of the entropic C function. Okay.
I'm sorry, the left-hand side of the inequality are the two quantities evaluated at different times.
Yeah, but it doesn't matter.
So inequality does not require different pieces are evaluated at the same time.
You don't have to evaluate them at the same time. You can use this inequality for any system. Okay.
But do you have the boundary of A and B changing in time?
So what do you mean by boundary?
The
you can, okay, so you can boost this line at this time slice if you want. And similarly, you can boost this slice into this time slice. And then you can see that it has with this.
Okay. The entanglement entropy is computed in the vacuum state, right? You define this vacuum state of field theory, so it does not change, and you can make the lines.
Yeah, I consider the stationary case.
Otherwise,
Right. Thank you.
A question. So the original Zamolodchikov C function for non-common field theory defined from the two-point function stress on the tensor. Does that agree with entropic C function?
No.
Away from,
No.
It doesn't agree.
No, it doesn't agree. Yeah, it has very different properties from the Zamolodchikov C function. So, yeah, thank you for asking. If we compare the Zamolodchikov C function and also the entropic C function, then both agrees with the central charge at the conformal fixed point. Okay, so this is the C function, and say this is linear by energy scale. So both start with CUV and reach that CIR. But okay, so Zamolodchikov C function always stationary at conformal fixed point. So it is stationary. So this is Zamolodchikov C function CZ. but the entropic C function can be divergent, or its gradient is divergent. It looks like this. So this is the entropic C function.
So how do you know that it's gradient divergent?
Okay, so I'm considering the massive scale, of course, the massive scale here
Free.
in 2 dimensions. And if you evaluate it explicitly, then you see the difference. So they are very different. Okay. So yeah, so both coincide with the central charge at 2 fixed points, but they interpret them differently. So completely different way. But both monotonically degraded, so you can use both or whatever you want.
Has there been any interacting massive quantum filter in 2 dimension where the entropic function is calculated?
I don't think so. I don't know any example. I know the free field examples. Okay, so this is the proof of the in the 2 dimension. But so now I'm going to move to the 3 dimensional case. But in 3 dimension there is no conformal anomaly, so it's not clear what we have to use in odd dimensions. So in even dimensions we had a conformal anomaly, and also you have central charge. So central charge is supposed to be a measure of degrees of freedom in even dimensions, but in odd dimensions there is nothing. So you can come up with several possibilities. So is there any C theorem in 3 dimensions? Naively, I can come up with 3 possibilities. So first one is a thermal C theorem. So where you put your theory at finite temperature and you compute the free energy of your system, then it should be proportional to T cubed from the dimensional counting analysis. And I will call its coefficient C therm. And you may expect that this one decreases along RG flow. And because in 2 dimensions, so you have T squared, and whose coefficient is equal to the central charge. So this is natural extension from 2 dimensions. And also, you may, I'm not sure this is called CT theorem, but I will call it CT theorem. So CT, so if theory is conformal, then if you compute the 2-point functions of stress tensors, then 2-point function of the stress tensor has an universal form, and so you have some function of x, sorry, this is rho sigma. So here you have some function of x, so this is completely fixed by conformal symmetry, and here so you have some coefficient which depends on your theory, and you may use this CT as a measure of degrees of freedom in any dimension. So the conjecture is that the value of CT at UV fixed point is always larger than that of air fixed point. And also in 2 dimensions, so this one is equal to the central charge. So this is also a very natural extension of the 2-dimensional C theorem to higher dimensions. Okay. And the final one.
So in the superconformal setting, do you just compute the superconformal index for 3D in this second case?
The second case.
Yeah.
See,
Because I remember Sanjay was talking about S2 that there's this ambiguity that's related to the central charge.
I don't think you can see a CT from superconformal index. So how do you read off this guy?
Yeah, I was just wondering if there's a...
I think if you put your theory on, say, Scarched 3 sphere,
Right.
and if you take a derivative with respect to the Scarched parameter, then you can see.
There you can see
Yeah,
the
yeah.
CT.
Okay, the third one is very non-trivial. So So it is called the F theorem. This is third option. The F theorem. And conjectured by Jeffries and his collaborators. Jeffries Clermont proof. Proof study. And also independently by Myers and Sinha. Yes. So the conjecture is that first you put your theory on 3 sphere and you define a free energy on 3 sphere. So F is given by minus log of the partial function on 3 sphere. And then they conjecture that FUV is greater than FIR. So this one is very non-trivial because you cannot come up with such a function from the extension to the C theorem. So you have 3 possibilities, but unfortunately, the first one has a counterexample. So counterexample was given by Sachdev, also 20 years ago. Counterexample by Sachdev. So he computed the C thermal for the Owen vector model, and he compared the value of C thermal at the critical Owen and also Goldstone phases, and then so C thermal theorem is violated. He used Owen vector model. Okay, so this one is gone, and but we still have 2 possibilities.
Sorry.
Yes.
What is F in this context?
F? Oh, this is just a thermal free energy.
Free energy.
It's thermal free energy. And not related to the partial function on 3 sphere. And second one, actually, I found a counterexample with my collaborator, Kazuya. In the context of 3D n equal 2 theories, so counterexample, so by myself and Yonekura. So we have found an example, counterexample, by using n equal 2 Betz-Limited model. So this one is also doesn't hold. So the third possibility only remains. Okay, so now I will focus on the F theorem. From now
So
on.
by counterexample, you mean it grows from UV?
Yes, it grows. Yes. Okay, by using the localization technique, you can compute the CT somehow, and you can compare the value of CT in the supersymmetric models.
So CT is going to be the log of ellipsoid partition function.
Yeah, you can evaluate CT by putting your theory on Scash 3 sphere and take a derivative with respect to discussion parameter. Yes. Anyway, yeah, there is a counterexample, so you don't have to care about it. Okay, so now, I'd like to focus on the third conjecture.
So has this been proven yet, or the third one?
Yeah, I'm going to prove it.
Oh, okay, all right, sorry.
Okay, so now I'm gonna focus on the third one, so F theorem in 3 dimensions. So this is the conjecture. So FUV is greater than the FIR. But here, so you should be careful because here I have a partial function on 3 sphere, which in general has a UV divergence. So here I'm supposed to use the renormalized partial function. So I think Sanjay talked about it in his talk. So usually, this one has a this is UV cutoff scale, and here.